Okay, last time we talked about the torque produced magnetic field on a loop. So got a current. And we find this. Anyhow, we find strip the magnetic fields out of the board. The forces on these two sides and just expand the loop. So as long as the loop plate is something strong enough to resist the expansion, it's not going to have any net effect on anything. Okay, there'll be a little stress in the material, but no force on this loop. Well, currents in this direction, magnetic fields this way, so we get quite a bit. Okay, currents this way, magnetic fields this way. So yeah, okay. Or if the magnetic field out of the board, we're not going to get any. It's going to expand them inside. Now, if the magnetic field is this way, then this side is parallel with the magnetic field, so is this one, no force. This side is perpendicular to the field, and now we do this and we find that there's a force in this direction. And then on this side, currents in this direction, fields this way, and the force is in this direction, so we're going to tend to rotate. I'm not sure I had the orientation all right when I did that. So about any axis, if this is my axis, you get the torque. I figured the torque based on an axis through one of the sides. And then I did it through the other side, and I found the torque was the same. Then I stated that the torque is independent of axis. For clarification, how's the torque due to the current and the magnetic field, not to anything else. And the confusion there was potential confusion when I was holding the board and producing the torque. The torques I was producing were against the gravitational field. So it'd be easy to think of this as being in a gravitational field. And if so, then the torque would certainly depend on where your axis is. Gravitational torque. Magnetic torque is not. And that's fairly easy to work out. So you get a non-zero torque about any axis parallel to the sides that are parallel to the magnetic field. And you just work that out with your right hand. Yes, I might have said something wrong about that. Anyhow, there we have it. Now, since we're talking about the torque here, we want to talk about the torque produced on a circular loop. Okay, so now I've got a circular loop. Got a magnetic field. So we've got a circular loop with a current I. With the circle, have radius A. We're going to center it at the origin. I'm not going to draw the X and Y axes. Actually, maybe. There's an X axis and a Y axis. We want to get the torque on a typical increment because, as usual, we didn't need to do integration here because the force on each side, we always have the same orientation with respect to the magnetic field along any given side. Okay. Here, the orientation with respect to the magnetic field is going to be different. So if you've got a magnetic field, so I'm going to be specific. I'm going to let B equal negative VJ. And make that uniform throughout the vicinity of the loop. So we'll take a typical increment. I'm debating whether I want to do this in polar or rectangular coordinates. I think we're going to rectangular. I'll make a typical delta SI. But the reason I was debating about polar it's pretty convenient to do this in terms of the angle. I'm just going to start with rectangular. Okay. Typical delta SI sample point. XI star Y video. Okay, now take this out of the picture and enlarge it. That'll be pretty close to straight line. I've got a little arc in it, to be honest. And here I've got the point. XI star. I can expect it. Okay, now I do have to have parameter for my delta S. I don't want to talk about the parameters. Okay, so looking for room to run this. The force is I times your L. It's IL cross B, right? Your L is gonna be your delta SI, whatever that is. Now, depending on where your increment is, the I delta SI vector is going to have an angle with the magnetic field that differs from other angles. Okay. Going to be I delta SI times B times sine of theta, where theta is your angle between B and your current element. So we've got here, we've got I delta SI, here we've got B. And here we've got our angle theta. If I know delta XI, if I know XI star and YJ star, I can figure out what that angle is. Because draw it again. Here's my XI star YJ star. Here's an angle that's for lack of a better choice. Actually, use that one, use alpha. This is the angle we normally call theta, but I'm using theta in my cross product, and it's not going to be the same as this angle. So this is going to be the angle alpha. Okay. Tangent of alpha is YJ star over XI star. And we're not actually going to use that, but let's say that for orientation. And we also got the idea that if we're in the second or third quadrant, tangent's going to be, well, tangent's still going to be this. Okay. The angle alpha will be the arctangent of this, maybe plus pi. It's not going to make any difference down there. Okay. So we got this angle alpha, and now we've got this direction here, which is our delta S sub I. What's the direction of delta S sub I? Well, it's perpendicular to this, so that its direction with respect to the x-axis. Well, it's going to be an arctangent of x over yj. Okay. But a negative, not like the negative precipitant. So, okay. If we come back down to our increment here, so again, so we can look at this angle. You can hear about Randall's potato. I think it's the easiest way to say this. Relative to what it shows, it probably could have thought through that. Yeah, that's gonna be. Okay, so probably made a bad choice when I tried to do this in terms of rectangular coordinates. You might just want to start on, because it's easier if I just use this angle. Because angle delta SI with this angle alpha is 90 degrees plus alpha. Or minus alpha. So let me stop it. I think that's a little better. Okay. I've abandoned my attempt to explain that. I realized in explaining it, there were too many relationships among these angles to make it really obvious. Okay. So we're back to this. Here's the torque. There's this magnetic field. Okay, maybe it's positive, maybe it's negative, we'll worry about that. Okay, the magnitude of the torque is this. I think Q is the magnetic moment of this current around the loop. The current being in this direction, the magnetic moment is going to be out of the board. So if this is X and this is Y, it's going to be B times Z. So the vectors be IBA squared times K. And I'm kind of waving my hand over this. It's mu cross B. For mu is IA squared K, and the torque is about the x-axis. Looking ahead to this, it's about the y-axis. This thing's going to rotate this way. Okay, if this is the x-axis, it's rotating, and actually it's a counterclockwise direction around the x-axis, isn't it? That'll be this. Now let's see if that works. If we multiply this by BJ, we better, yeah, negative I. Multiple negative I, and we do. Okay. If we do K times J, here's K, there's J, there's negative I, right? So this is all consistent with the negative side here. It's consistent with what we see. So let's make sure we see what this looks like. Imagine again, this is a square loop. Now our X direction is going to be this way, our Y direction is going to be this way. Here's our Z direction. Current is going in the positive K direction. Okay. On this play, now magnetic field I'm drawn is in the negative Y direction, this direction. So the field's this direction, the current's this direction. Current cross field. Current here. Cross field is this way. So this is going to be pushed down. Opposite direction of the current here means this side's going to be pushed up. So things going to rotate like this. This is the X direction. We're rotating counterclockwise about the X-axis, or about an axis parallel with the X-axis. Counterclockwise rotation with respect to the X direction. Okay. So that the rotation is in the negative I direction. And that all works out these definitions. Okay, so what's the significance of A squared? It's the area of that loop. Okay. Now, what we were going to get with that circle. Do have a problem with the directions. We'll have to resolve that. Because your magnetic field would have been negative BJ, wouldn't it? So everything I said. Well, that's how we think it through. I'll think it through again. Not worry about it right now. But okay. So again, if we have B equals negative BJ. You know, B equals negative BJ. Area A, current in positive direction. Then magnetic moment is again current area. And I was going to derive that. Been better if I would have started with theta as my parameter, but I don't want time to start all that over. Right now, we're just saying that if you do the integral, you get this. And it really generalizes any closed, non-intersecting loop. Okay, both of these, this one which we pretty much derived, this one which we abandoned deriving for the moment. And I'm not sure your text derives it either. It's not difficult, but it's difficult to explain. So I should have figured out better how to explain it. Again, in both cases here, B is assumed to be parallel to the loop. Okay. If B isn't parallel to the loop, then what happens? Well, let's just think about it. Let's think about it in three dimensions with our standard loop. Okay, so here's a loop. And let's say now the magnetic field. Now, if the magnetic field's in this direction, it just tends to expand. Okay. If it's in this direction, it tends to contract. Okay. That's easy enough to see if you just use your right hand. If B is between this direction and this direction, it makes some angle theta with the loop. And I'm going to take a quick, excuse me, quick peek at the book to make sure that I'm using the same symbol they used. I'm pretty sure it was a theta, but I'm going to put my glasses on and make sure. Okay, hopefully back to focus. Yeah, that's good. Okay, so in three dimensions, what we want to do again is we want to consider what happens if B isn't in the plane of the loop. So we're going to put a loop there, and I'll just put the loop in the first quadrant. Square loop, because it's easy to draw. Do it anyway, and we got the current. Again, flowing in the counterclockwise direction. So that mu equals I times the area times K. We have a magnetic field. B. Making an angle phi with mu. We want B to be parallel to the YZ plane. Okay, I guess that's what I'm going to write it. I was trying to think of a better way. It has no X component. Some B equals AI plus B equals BXI plus BY, whatever. And that's so we can simplify calculations. We don't have to do it. Okay. We'll take it. Rather than do just a small increment, we take a whole side. So let's just look at this side here. So the right hand side here, three dimensions, and I can draw my vector for B. It'd be more convenient. It'd be easy to look at. If I draw B like in this direction, not put parallel with this. But now here's my Draw my vector. Side of length A. Implicitly, this is the same loop that we have there. Sides are length A. Maybe I just want to draw that vector. Okay, and then I have my B, which is conveniently the direction that it's right through my label. Okay, so here we have negative IA times I. And here we have V. So what's the angle for this and this? Well, this is in the XY plane. And V is perpendicular to the x-axis. So that the angle here is going to be there. And again, you can visualize that if we look our loop. Whoever drawn it is like in this direction, perpendicular to the x-axis, so it's in parallel to the YZ plane. So we take it with this side, and right there is our angle. Okay. With the I vector, make sure I got that right. Here's our I vector. Okay. And it's going to be pi minus theta. The angle is pi. Wrong, the angle is pi with mu. So here's mu. Here's pi. Okay, let's work this out. Your force, okay, but turns out straightforward as heck. B is parallel to the YZ plane. This side is in the X direction, so that this angle is the right angle. So doesn't look like a right angle because we're at a weird angle with the whole thing. The way I've drawn the XYZ. Okay. The force is going to be perpendicular to B, perpendicular to IA times I. I'm going to have to get B. Try to avoid doing that. Okay. And it's BYJ plus BZK is perpendicular to the X. Okay, so my force is negative IA times the I vector across the V vector. Well, let's write that as BYJ plus BZK. Then I cross J is K, so negative I cross J is going to be negative K. So we're going to get a negative IA V sub Y times K. And then I cross K is negative J. We have a negative under the IA. If now we look at plane, okay, our B is in this direction, our I is in this direction. IA cross B. Gonna have to get our hand in an impossible position. Got to push my hand around this way. And I'm going to find that the plane perpendicular to IA and B is normal to a vector that goes down this way. So if this is at 30 degrees, cross product is going to be, it'll need to be 30 degrees out. Okay. And that's the key. My force again going to be IA. Got to turn the IA this way so we can cross it with B in this direction, B's in this direction, I in this direction. So to turn our fingers to IA, B, we've got to go. If it's 90 degrees, the force okay, force is going to kind of go down like this. Where this is the horizontal direction. You got that here. And of course, you can compute the angle easily. The angle is just going to be this vector is in the YZ plane. And the angle with the Y direction is going to be the inverse tangent of negative BY over BC. Okay. There's something. Coming back this way, force is going to be like so. Now that force has a component in the J direction that only tends to push these sides apart. Only tends to expand the loop in the wrong direction. But it also has Z components. And the Z component of this force tends to push this side down, tends to push this side up. Okay, that's where the torque comes from. Now it's going to turn out, I don't want to go through any more details here, but keeps turning it up. But it's only a component of the force that produces a torque. Okay. So K component of this side is equal and opposite. So this side, the current's going this way. And you're going to have this. Okay. These components produce the torque. Torque still going to be off the x-axis. Okay, and going to be like this. The component of this force is going to push down here. The component of the force on this side is going to push up. You're going to get a torque in the counterclockwise direction about the x-axis. And the whole point of this now is the torque. Well, the torque is going to be negative IA squared Vy times the I. That's assuming you're rotating about the x-axis, so that only this force produces a torque. If you're about this axis, then force over here is going to produce the torque. If you're about some other axis, they'll both produce torques, but it'll all add up to the same thing. Okay, so there's your torque. And of course, that's your I squared your mu, moment inertia. I'm just going to do the scalar. It's going to be UV sine phi. It's because look at this direction. Oh, yeah, okay. If this is phi, then here's Vy, here's Vz, and Vy is equal to this vector B. Yeah, it's phi. Vy is B sine phi. Okay. So what it comes down to is because of this angle with the plane of the loop, due to that angle, you get less torque. And that's because this force has two components, and only one component produces torque. That's the bottom line. All this other stuff is just one way of getting it. It's equivalent to saying that your torque is U cross B. It's getting the angle between B and phi. The definition of cross product. Magnitude of this is just this times the magnitude of this times magnitude of this times the sine of the angle. I took way too long and I didn't give you good explanation. I really apologize for that, but that's what it comes down to. Okay, so magnetic moments are really important. Okay, for example, you study chemistry. You have your quantum vectors, your N, your L, so forth, right? Well, you have a magnetic component that corresponds to the alignment of the orbit with the magnetic field. So you put a magnetic field on a gas. Okay, we've got tubes over there. We got gases. We put it 50,000 volts through the gas. So we have that electrons running down through the gas, exciting the gas, and so forth. And we can measure the spectrum of that gas. Okay. We put a magnetic field on it, put it inside of a pair of Helmholtz coils with a lot of current. And the field lines, spectral lines, shift. We get multiple spectral lines because of the alignment of the orbits of the electrons. They don't really orbit, they act like they. Okay. Because the way those align with the magnetic field, align this way, you get a little more energy. Align this way, you get a little less. Now we haven't talked about spectroscopy or anything like that, but it's kind of neat stuff. Okay. Okay, well, there we have that.